Good morning, Earth Science kids. We're going to be talking quickly about deposition today. Deposition is the dropping of sediments picked up by agents of erosion. So water, wind, ice, they pick up sediments. When they get to a situation where water or wind slow down, they're going to begin dropping those sediments. For ice, of course, it has to melt for it to begin to drop the sediments. So the major factors affecting deposition: the particle size, particle shape, particle density. All right. Of those, the particle size are going to be the real players here. If we look at the sedimentation tube, all right, if we look at the bottom of it, when this was dropped, we see larger sediments and then grading up to smaller and smaller sediments. The smallest sediments still have not settled out yet. So larger sediments will always tend to settle out first. After that, you have the particle shape and the particle density playing a big role there. But most particles are similar in shape and density, so they play a lesser role. The smallest things like ions, they'll settle out when a solution becomes completely saturated with them. If you evaporate seawater, that'd be an example of supersaturating the solution with salt, and so salt will actually like snow salt in the bottom of that ocean. If you are talking about shape, it makes sense that round particles settle before flat particles. Flat particles will flutter, round particles head right down. Right? Friction between the water will slow the particles down. Round particles settle faster. That's all you really need to know. More dense particles obviously would settle faster. If we talk about panning for gold, this is a gold pan. See the ridges here? So you scoop up some sediments and get the water slurrying around here and pour it out. On the ridges, gold is so much more dense than anything else, the ridges will end up holding little tiny flakes of gold. So the major agents of erosion are also the agents of deposition. Water and wind being substantial agents of erosion, also therefore deposition. Gravity, whole landslides could pull things down. And of course, glaciers. Wherever glaciers have been, the land has been seriously carved by them. So water, major one. A decrease in water velocity causes the sediments to settle out. Sediments that are deposited from water are sorted according to size, shape, and density, primarily, of course, size. As water slows, the biggest ones settle out first, and you go from big right down to small. So when we talk about horizontal or vertical, horizontal being this way, a stream slowing down as it empties into a lake would do that. Or if you had a massive flood all into a lake, that would then sort it vertically, so you would have layered bedding. So horizontal, the largest, roundest, densest settle out first, and the other ones settle out next. The things that are dissolved in there require the water to evaporate. Any river delta is horizontally sorted. The largest particles are going to be where the water empties in and begins to slow down. The smallest particles will be further out into the ocean. So this would be an example of horizontal sediment sorting, and you can see the large particles, and then it gets finer and finer and finer as you get further offshore. So for vertical sorting, if the sediments are just dumped into calm water, they would be vertically sorted. So you'd have the largest, roundest, most dense would be on the bottom, and the smaller ones would be on the top of that. And if you can evaporate it, then on the very top, you'd have the colloids and ions. So you could do this. There's a sediment tube, and if you shake it, sure enough, you get the largest particles settling out first. So this shows examples of vertical sorting, and each layer would be a separate event. So if a landslide were to dump into a body of water, that would be vertically sorted, right? On the continental shelf, that occurs. Sediments build up along the shelf, and they're heavy enough, and they slide down. These are turbidity currents, bizarre things underwater, like a mudslide underwater. So this is like the chart we use to find erosion, and in reverse, it's deposition. So as the water slows, you can see what particles it begins to drop. So what's the largest size deposited when 200 centimeters per second slows to still water? Well, if we go from 200 centimeters per second, probably easier doing it from the top, go down. Oh, look at that. And so this would be cobbles. And if you needed to, you could even read the actual size. So if the river can't carry sand, what other pieces can be carried? Well, if we assume that sand is, nope, you can't carry sand, that would be the limit of the particles you cannot carry. Well, you still could theoretically carry silt and clay. So as the sediments settle out, they're vertically sorted. Episode after episode causes something we call graded bedding. Now, geologists use graded bedding to determine whether a rock unit is upright or not. If you're talking about this fossil, then this fossil, then this fossil, you need some way to prove that the rocks have not been overturned, because that occasionally happens. That would mean everything you're saying is backwards. And here you have an example of graded bedding. Large grains there, smaller grains there. Then we have large grains there, smaller grains there. Kind of makes sense. If you look at it, it just stands out. Well, wind carries sediment also. So as soon as the wind begins to decrease speed, the larger sediments settle out first, the smaller settle out last. This causes cross-bedding. Cross-bedding in sand. So when you see rock that has that, and you see a lot of sandstone that has that, you know you're looking at a fossilized sand dune. How cool is that? When particles are pulled down by gravity, they all fall at the same speed. So all the particles arrive at the ground at the same time, so no sorting can occur. You need a medium like wind changing speed or water changing speed. Things just falling, they all fall at the same speed, so it doesn't help. Deposition by glaciers occurs when a glacier melts and drops its load of sediment. As a glacier scours the valley floor, it picks up vast, and we're talking vast amounts of sediment. It just rips everything up and tumbles it inside the glacier, so the glacier is filled with garbage. Look at that. So that would be the melting edge of a glacier, and you could see all of the various forms that would be left behind. Here would be the terminal moraine, the farthest the glacier ever went. These were old terminal moraines that then got overrun by the glacier again and turned into drumlins. We have all sorts of lakes here for a variety of reasons. Some are kettle lakes, where a chunk of ice in the ground moraine melted and left a pool, but very often you have moraine dammed lakes, where the pile of glacier garbage forms a dam and doesn't let a lake empty out. Neat stuff, all sorts of interesting glacial things. Notice that you also have places where you have braided streams. Now, what's a braided stream? Well, water is pouring out of the glacier to carry so much junk with it that it can't help but overfill its stream bank and then push the stream back and forth. So the stream is constantly having to play through the tremendous amount of sediments in there. If the water has worked it, those sediments are sorted. All the other sediments that have not been worked by water, just dumped by the ice, they're just a mess of all the different sizes. So in terms of glaciers, the type of material deposited, drift any material left by the glacier we call glacial drift, and we have two kinds. The glacial till is just a big pile of glacier garbage. It's unsorted, but the glacial outwash, that was caught in like a stream, and it was sorted. So till, all sediment sizes found together, huge piles in front of or along the sides of glaciers. So you have lateral moraines and medial moraines. Lateral moraines are along the side of the glacier, and as it goes down through the valley floor, it grinds up the edges of the mountains and fills with debris there. The medial moraine is in the middle, and from this picture, you can kind of see how that would be made as the glacier comes down and these two glaciers meet. The sides of them meet right in the middle and form the medial moraine. So if you count how many medial moraines you can find at the end of a glacier, you're able to count how many different glaciers move into it way up valley. Huge moraine there. If you look carefully, you can see cars here and get a sense of the size of this. The actual glacier is over here. So, and notice the U-shaped valley up here that the glacier is pouring down from. So get a lot of glacier stuff here. Notice also the glacier pouring down from the side of the mountain there, adding into the valley glacier. Glacial outwash are just the sediments carried by the glacier that are worked by water. So they're all sorted. So the sediments would be horizontally sorted. The larger sediments deposited near the front of the glacier, the smallest farther away. So here is a glacial valley. The two glaciers you see way behind me there, the one over here is, oh, that's got to be a mile away or more. This is a good half mile away at least, and I might have those distances wrong. All the distances when you're looking out here are, if you're new to being out west, the distances can be very confusing because the air is so much clearer. We just don't expect you to have such clarity looking at something when it's so far away. But this huge moraine here is also, that's got to be probably half a mile away, quarter mile away. I don't know. It's a long distance away along the valley floor. So this is the outwash plain that I'm walking on. All the particles are sorted. That's the moraine. And that is one very happy glacier guy. These are beautiful places to be. All right. Thanks for watching.